Well, hello everyone, and welcome to this Windpower Engineering and Development webinar, Working Toward a Smarter Grid. I'm your host, Paul Dvorak, editor of Windpower Engineering and Development magazine. Thank you for joining us. Now, just a brief agenda before we really start. The webinar will be available at windpowerengineering.com, and the link to it and the slides will be mailed to everyone who has registered. At the end of the presentation, we'll have a brief question and answer session. Okay. Of course, not everyone who wanted to attend the webinar could do so, but you can help them learn from it by tweeting key points and the takeaways you think important. In your tweets, be sure to include the hashtag WindWebinar. Now, after the presentation, I'll read the questions that you and the audience have submitted. And you can do that by typing them into the questions box on your GoToMeeting panel that should be on the right of your screen. Now, I'd suggest you type the questions into that box as soon as they come to you rather than waiting to the end of the presentations. And then we'll try to answer as many as possible before the hour is up. Now let me tell you a little about our speakers, and then I'll turn the microphone over to them. Our first speaker is Roberto Piacentini, and he's a senior manager for strategic business development for National Instruments Energy segment. And in that role, Piacentini manages large, complex programs in the energy, utilities, oil, and gas industries worldwide. His responsibilities include senior-level leadership for structuring customer solutions and communications liaison to customers and executive sponsors. Recent collaborations include working with smart grid customers on distribution control, substation automation, distributed monitoring, and asset management. And our second presenter is Dr. Daniel Kamiński. He's with the company ELCOM AS in the Czech Republic, where he's talking to us for now, so kudos to him for that. It's late in the evening for him, so thanks for being here. There he co-founded the division of virtual instrumentation. Dr. Kamiński received his PhD in power engineering in 1992. From 97 to 99, he led the software development team for the first generation of ELCOM's power quality analyzers, one of the first instruments running firmware, completely written in LabVIEW. He also manages that the division of virtual instrumentation, a National Instruments Alliance member, delivering products and services in the area of virtual instrumentation worldwide. Dr. Kamiński is also the chairman of the supervisory board for the Ostrava Science University Park in the city of Ostrava. And with that, we'll start with Mr. Piacentini. Roberto, the floor is all yours.
Thank you, Paul. So let me make sure that I got the control here. Okay. So hello, everyone. So just before we get started, I just wanted to spare a few minutes just talking a little bit about National Instruments for those of you who don't know us. So basically, National Instruments is headquartered in Austin, Texas. We were established in 1976, and as of last year, we crossed the $1 billion mark for our revenues. One point I want to make in here is that we are a heavily focused company on engineering, and we invest from 16 to 18% of our revenue back into R&D. In fact, if you look at the numbers for 2011, we were actually a little bit above 18, maybe close to 20% of our revenue invested back in R&D. The key point is that our mission here is that we equip engineers and scientists with tools that not only accelerate productivity, but also innovation and discovery. We operate in areas such as test, control, measurement, automation, in a variety of industries, all the way from energy to aeromilitary, automotive, research, and academia. With that, I want to move on to the guts of this presentation and talk a little bit more about how we can modernize the grid with distributed intelligence and smart grid-ready instrumentation. First of all, I wanted to talk a little bit about some industry trends. So the first bullet I have in this slide is the future of global power generation. There's a lot of research that show that by 2020, half of the world generation are going to come out from emerging markets like India, Brazil, China, and so forth. Now, about 1/3 of the energy produced in the world is going to be from renewable as well as nuclear. We're going to see a resurgence of nuclear in the coming years as well. In terms of water and environment, we'll see increased stress and concerns about the quality of the water and how sustainable the water as well as wastewater treatment are. In terms of innovating to zero, what I mean by that is that we'll use new technologies and novel approaches to drive towards zero emissions, zero accidents, zero fatalities, zero defects, as well as zero security breaches. One important point, I'm going to talk a little bit more about that, is that as we put more of this computerized devices on the grid, security becomes a very, very important aspect that we have to take care of too. In terms of smart cities and measurements, we'll see that we're going to instrument the grid a lot. We're going to have a lot of devices monitoring the grid, controlling the grid. The smart cities will be cities that can respond very quickly to disturbances and automatically heal from these disturbances in the grid. In terms of measurements, we'll see a shift from traditional instrumentation more towards embedded flexible systems. And I'm going to talk more about what I mean by this. And lastly, and certainly not least, global economic decline. This is something that's going to hit us again. And honestly, what it means is that we'll have shrinking budgets and resources, which ultimately is going to favor high efficiency, multi-purpose, field programmable instrumentation that can evolve as our needs evolve. So now, if we talk a little bit about the challenge we're facing today with our power systems, the first thing that comes to mind is access to electricity. Our infrastructure was built back in the 1900s, and it had a completely different use case in mind. On top of that, we have a rise in domestic electricity consumption. We see what we call MELs, M-E-Ls, which are miscellaneous electronic loads. And the challenge with this type of devices is that it's very hard for us to predict the use of this, or when are going to be peak of users of this type of devices. Next, poor reliability and reactive maintenance. As I mentioned before, the grid was built with a completely different use case in mind. It was built for incandescent lights, heavy machinery, and really not for computers. This new type of lights we have, like fluorescent lights or LED lights, as well as certainly not for hybrid electric vehicles as well. There's also a lack of infrastructure for integrating renewables. This is, as I mentioned in the previous slide, about a third of the power generation is predicted to come from renewable sources such as wind and solar. So we have to figure out a way to integrate this renewable sources, which are very hard to predict as well. It's hard for us to say when there will be sun or wind in certain parts of the world. So we have to come up with devices or solutions for large-scale grid-tied storages. Next, we have smart grid is a term that everybody uses for whatever project out there for modernizing the grid. What it really means is that utilities are learning, or all of us are learning as we go. So flexibility is paramount. It's very, very important that devices that we put to modernize the grid are able to evolve as the needs evolve. Along those lines, technology and standards, they're also constantly evolving. And we have to keep in mind that the traditional approach for instruments, whenever a manufacturer creates an instrument, it's designed with a given time in mind. So then standards and technologies is locked in time. So this enhances the risks for obsolescence in the future. Now, if you look in terms of the various devices we have today to measure, to visualize, to automate the grid, we have things from the top right of the screen, such as reclosers and sectionalizers that are used for protecting our grid. We have other devices such as smart metering devices to measure how much energy is used, as well as allow utilities to connect and disconnect very quickly and remotely users from the grid. All the way to the far left, devices such as Phasor measurement units, which give us very good insights, real-time insights on grid stability and grid health. Now, if you look closer to these devices, we'll see that we have hundreds of these devices out there with multiple protocols, multiple buses, fixed functionality. And this is a very important point. This fixed functionality, it's something that probably contributed to where we are today, which is those devices cannot evolve as our needs evolve. Hundreds of vendors raising interoperability issues. And on top of that, all of these different vendors, they have their own data visualization tools, which makes it even harder for people to deploy these devices, have the devices talk to each other, and later on analyze the data produced by those devices. If we could start over, let's talk a little bit about what would be the key requirements for what I'm calling here this is smart grid instrument, right? The first item that comes to mind for this ideal instrument is distributed intelligence. Distributed intelligence is when you push the decision making to as close to the nodes in the field as possible. So this promotes optimal network response times because the data is captured, processed, and actions are taking place right there versus getting this data, sending to a central location for processing and taking decisions. it also allows unprecedented amounts of data to be processed. Imagine that in the future, I mentioned that we'll have a lot of these devices in the field, making measurements, controlling the grid. Imagine that all these devices are streaming data back to a central location. This is probably going to clog not just wireless networks, but even wired connections to those devices. By pushing the intelligence to those devices, you don't have to be streaming this data all the time back to the SCADA system. You can take this data, process the data, take actions, and maybe just send back to your SCADA system what is really important to you: alarms, events, maybe the waveform that you capture for a transient, things along those lines. And it also helps with reliability, because it's a decentralized coordination. It's not just one point of failure, like just your SCADA system fails, the whole system goes down. You are pushing the intelligence closer to the nodes in the field. Second, flexible communication protocols. In the US, we use DNP3 very widely in the US. In Europe, it's more towards 6.870. And there is this holy grail that is coming up, which is called 61850, 61850, which is a communication protocol that is promised to unify the world in terms of energy-related communication protocols. So we need to have a device that is able of evolving their communication capabilities or protocols without having to replace the asset. In terms of future-proof architecture, we have to think in terms of, okay, what would be the ideal device for preventing us from being, again, where we are today with our traditional instruments 20, 30 years in the future. First of all, real-time platform. We want to be able to capture this fast-moving data, such as transients, line disturbances. We also want to have a measurement quality and get the right granularity for the waveforms, for the disturbances we are capturing in the field. And for that, we need high-fidelity analog-to-digital converters. We need common file formats to help with the interoperability issues I mentioned before, such as ComTrade, for example. And we want to be expandable, as well as allow remote upgrades. We don't want to have to replace the asset in the field every time there's a need for a new feature or new function. The other important point, as I mentioned a little bit before, is security. As you're putting more and more computers controlling, managing, monitoring the grid for us, security becomes a huge concern. The last thing we want is to have like a bad intentioned person taking control of the grid and doing bad things about it. So we need to comply to standards like the NERC SIP. NERC, by the way, stands for North America Electric Reliability Corporation, and SIP is Critical Infrastructure Protection, which have extensive library of standards and recommendations for how to protect your devices, your instruments. Now, if we look in terms of, okay, we know what would be the ideal device we wanted, right? So let's see, how can we make it happen today? Well, from one side, we have computers. Computers are very powerful. They are open source, expandable, and most important, programmable, software-defined. They can evolve as the needs evolve. On the other end of the spectrum, we have the traditional transmission and distribution instrumentation, which offer the measurement quality we want, embedded, reliable, robust, standard-based, but it's fixed functionality. It's vendor-defined. So we feel there is a gap between these two worlds. This ideal device that I described in the previous slide seems to be a gap today. We need the best of both worlds. We want something that offers measurement quality, embedded processing power, it's reliable, robust, open source and programmable, and above all things, is software programmed or software defined. We want to be able to evolve the functionality of this device as the needs evolve. Now, one of such technologies that we believe can help us close the gap between these two worlds and help us create this ideal instrument is called FPGA. FPGA stands for Field Programmable Gate Array. And for those of you that are not hardware engineers, I'm going to explain a little bit what this technology is. Let's go back a few years before FPGA existed. If you're a hardware engineer and you wanted to develop any hardware, a phone, a computer, a traditional instrumentation, you would go to your drawing board, you use complex tools such as VHDL, and you would literally burn your algorithms that you developed on the silicon, and then you create the chip. Once this chip is created, you just take this chip and then you stick it on your device, your smartphone or computer or traditional instrument, whatever you want to put it there. Later on, if you found a bug in the algorithm that you programmed in this chip, there's no way to correct it. You have to go, recall all these devices, and physically replace the chip with a new chip with a fixed algorithm. What FPGA did for the industry is that it allowed these hardware engineers to no longer burn their algorithms on the silicon. Basically, the FPGA, it has inside this chip, it has programmable interconnects, configurable logic blocks, as well as I/O blocks that you can reconfigure it. So those hardware engineers designing today smartphones, instruments, any electronic device, they use the same complex tools such as VHDL, which is a programming language for hardware design, and instead of burning their algorithms on the silicon, they simply download a bit file, as we call, to the FPGA. The FPGA chip behaves exactly as the old-time chip, but with the benefit that if there is a bug in the algorithm, they don't have to recall anything. They simply download or push out a new firmware or a new bit file to that chip, and the new algorithm is there. What National Instruments did, we actually brought the FPGA technology for everyone. We don't want anybody to become hardware engineers or have to learn these complex tools to leverage the benefits of the FPGA platform. So basically, using LabVIEW, our graphical system programming tool, which is depicted on the bottom left of the screen, you can actually design your algorithms with very easy to use, intuitive graphical tools. Now, LabVIEW behind the scenes will convert your algorithms into what we call the bit file. So it compiles it, synthesizes it, configure all the logic blocks on the FPGA, and deploys your algorithm directly in the FPGA. What we gain by executing code on the FPGA is, number one, performance. There's no operating system. Any algorithm, protection algorithms, or measurement algorithms that you put on the FPGA runs directly on the chip. It's very programmable. As I mentioned before, you can change it. You're not burning anything on the silicon. You're getting the performance of a hardware silicon, but without the fixed approach. And you also get reliability. Like I mentioned before, there's no operating system here. It's only your code. Now, one of the platforms that offers this FPGA technology is called CompactRIO. So CompactRIO is the National Instruments FPGA-based platform. It's extremely ruggedized, supports minus 40 to 70 degrees of temperature, 50 G shock, 5G vibration, and very low power consumption. At the heart of the FPGA of CompactRIO, we have an FPGA. So this FPGA is connected directly to the I/O modules, which we have a variety of different modules there for voltage measurements, current measurements, digital, a variety of different modules. And the key thing that I want to depict in this slide is that note that all of these modules are directly connected to the FPGA. So we can have very fast, in the nanosecond range, closed loop control applications. So for protection, this is very important, a protection algorithm. You can make all the measurements, the analog measurements in here, process them on the FPGA, and send out commands for opening, close, or actuate on circuit breakers and so forth. And keep in mind that there's no operating system on the FPGA. So your code is extremely robust. Now, just to make this platform a little more flexible, we added a real-time processor for things like maybe analysis, maybe measurements that are not so critical, additional connectivity such as communication protocols like 62050 that I mentioned before. The bottom line is that this FPGA-based platform provides this flexible instrumentation or this flexible approach that I described before that allows us to adapt our instruments to changing requirements. So we strongly believe the FPGA is really the answer for bridging these two worlds, the computers as well as the traditional instrumentation on the other side. Now I want to walk us through a very quick example of a virtual instrument utilizing this FPGA approach that I described in the previous slide. So basically, what is a phasor? And what is a phasor measurement unit? A phasor is a very simple measurement. Basically, we know that in our power grids, we have sine waves going there. So a phasor is pretty much the phase angle that we have, which is depicted on the left side of this screen, and as well with the amplitude. What a phasor measurement unit does is simply measures that. It measures the phase angle as well as the amplitude of the sine waves we have on our lines. Now, with just one PMU or phasor measurement unit, it doesn't give us much information. The interesting thing starts to happen when you have multiple PMUs on your grid. When you have multiple PMUs on the grid, you can measure the phase and the amplitude of two distinct points in the grid. And we know that the energy flows from a higher angle to a smaller angle. So what we get, we can create a very nice graph like this, for example, that is depicting the west coast of the US with the flow of energy. So then by placing all the different PMUs out there, you can measure where the electricity is flowing and for example, shut down nodes that are consuming too much energy. One other thing that you can monitor is the rate of separation of these angles, how fast these angles are separating from each other from two different points, and also predict when the grid is going towards an unstable state, and then cut out those nodes before it becomes a system-wide collapse and a blackout. Now, in terms of the FPGA approach, as I mentioned before, a National Instrument has a Phasor management unit device that is based completely on this FPGA architecture I described before. So on the FPGA side, we put all of the data acquisition, timestamping, filtering, and any custom IP that you want to put in there. Now, the FPGA sends this data to the real-time side for actually calculating the Phasor measurements and also communicating with the PDCs, the Phasor data concentrator, utilizing the C37118 communication protocol. Now, imagine, as I mentioned before, that you might want to add additional measurements, or your requirements might change. A PMU is a simple device, right? So imagine that you want to add additional things to this device because this is all defined in software, and here is a picture of the code behind the PMU. So this is all done in LabVIEW, our graphical system design. So you have the ability to modify this. And because we are offering the source code for this, one quick example here is GPS. GPS is a critical piece to PMU. So basically, any measurement you make with a Phasor in these various points of your grid has to be synchronized, and we use GPS for synchronizing it. But GPS comes from space. The signal comes from space, a very weak signal, and can be very easily messed with because of a cloud or because there's interference from other frequencies. So imagine that because you have access to the source code of this PMU, you can get directly on the portion of the code that is receiving the GPS signal and monitor when this GPS signal is no longer valid or it's been spoofed with. And you can add algorithm or IP in here that will switch from maybe the GPS source to another source more reliable than GPS, such as, for example, a Rubidian clock, for example, here. And if you want to change even further, add more functionality, like power quality measurements, for example, you can actually do it as well. You have this is just an example of some measurements that you might want to make. Those are power quality measurements. All you have to do is put this in your computer, recompile your FPGA code, and download to the PMU, boom. And then you have now a PMU that makes power quality measurements as well. In a nutshell, the key benefits or strengths of this FPGA platform is the measurement quality, computing power, as well as flexibility. Now, if you translate this into industry terms, what you get by measurement quality and computing power is better fault location and prevention. In terms of flexibility, this means install once and upgrade remotely, and this is very key. This is going to prepare us for the future. Those devices that allow us to change their personality will help us not be where we are today 10, 20, 30 years in the future. To summarize, some key takeaways. There's really no silver bullet when it comes to modernizing the grid. We have to remember this approach, the virtual instrument approach versus the traditional approach. Most likely it's going to be a continuous effort. I'm betting on the virtual instrumentation side. I believe that this flexibility is going to be paramount to help us continue to evolve the grid. A smart grid-ready instrumentation is simply a device that allows us to change its functionality completely, not just configuration. You can change completely the functionality of the device without having to replace the asset. And PMUs, as I described in the example, are very interesting devices that give us this real-time assessment of the health of the grid. And it can really help us further integrate sources such as wind and solar into the grid. Because as I described before, this renewable sources are very unpredictable. We don't know when there'll be sun or wind out there. So then by using this PMU technology, we can use to synchronize when to put in and out this energy and how to synchronize this generation with our grid in the field. So with that, I'm going to transfer control to Dr. Daniel Kaminsky, who's going to talk to us a little bit more about power quality and the PMU case study.
Roberto, I hope that everybody hears me, and I would like to spend some time talking a little bit about the solutions which we have prepared for the market, for our customers using National Instruments technologies, and the knowledges that we have gained over last 16, 17 years, and maybe being based also on the knowledges coming from the company ELCOM, which is the Czech-based company. Okay, so let me to say a few words about the ELCOM company. So we are a Czech company, as I mentioned before, so located in Europe, and we were founded in 1990. Probably I can add one detail that we were celebrating yesterday, 22nd year of existence on the market, as we were founded in 12th of December 1990. At the moment we have 5 divisions. It's applied electronics, drives and motors, realization and design, virtual instrumentation, which is the division where I work for ELCOM as a director at the moment, and manufacturing division. The core business of ELCOM was used to be electrical engineering, but today there was added also the instrumentation, which is represented by the virtual instrumentation division, which was founded in 1997. So this is the reason why I was saying that we are currently having there's more than 15 years of experience in the test and measurement automation and the design and development of the measuring instruments, mainly for the area of the power and the grid monitoring. So let me to talk a little bit about the electricity in the beginning. So what is specific for the electricity, and how we can look on the electricity as a product. So electricity has some specifics. It cannot be stored in a quantity like we are used for any other kind of the product. When we speak about the product, so we typically mean something what we can hold in our hands, what we can see, what is visible, what is having the weight. So all that is not applicable for the electricity. On the other hand, electricity is one of the most important product ever, and we cannot imagine our life without the electricity. I guess that almost everybody sometimes faced the blackout. So faced the situation where there was no electricity available. And it's a great time from some certain perspective to really understand how we can not live without the electricity, because almost everything stopped to work. So the computers are not working, the light is not working, so the heating system is not working, the air conditioning is not working, the TV set is not working, so we cannot use our radio, for instance, if it's not powered by the battery. So almost everything is impossible without the electricity. So the importance of the availability of the continuous availability of the electricity is extremely high for our everyday life. Another specifics listed on that slide can be said as they are said in this bullet. So it's electricity is generated quite far away from the point of use. It's fed to the grid together with the output of many other generators. So basically, we don't know which is the power plant which is feeding us with the electricity, but we are quite sure that there is some of them. And we of course know that it's not just one power plant, but there are many around us. And all of that are connected into the grid. And also the connection between the power plant and our home is not just a simple wire. So it goes across to quite a couple of different voltage levels, quite of a different grids that are interconnected by the several transformers, and the length of the cables of the wires are quite long. It's a lot of miles, a lot of kilometers. But even if all of that applies for the electricity, we can still look on the electricity as a product where we can define the quality. And if you look on the slide, which is currently on our screen, so it's showing the basic parameters that can be treated as the quality parameters. So for instance, if the voltage is in the level as it is required, let's say 110 volts, if we plug in the oscilloscope into the standard power outlet that we all of us are having at home, so we should see the sinusoidal waveform. If we measure the frequency, it should be 60 Hertz when being in the US or 50 Hertz when being in Europe. And if we have some free-phase appliances, so we just simply expect that the electricity is available continuously with all that parameters mentioned above in all three phases. And the main thing that it's permanently available. Let's have a look on the picture which is in the middle. It basically shows the situation of the power plant being connected to our home across the transmission part of the grid, the distribution part of the grid, and the feeders which actually connects our home with the last transformer, transforming down the voltage to the level which we expect to have, let's say 110 volts or 230 volts if again being back in Europe. So all the parts of the grid are having some power quality issues. So for instance, the generation. The generation issues connected with the power quality might be the interaction with the close couple loads, for instance, or the harmonics coming from the loads. Basically, many of the appliances, many of the loads which are currently connected to the grid are non-linear loads. It's not just the simple resistors, for instance, like it was a couple of decades before, but today almost everything is being powered by some certain let's say thyristor converters or some switching units which is driving or controlling the amount of the power which goes from the grid to our appliance. And when we switch something, it typically generates a lot of higher harmonics. Excuse me, please. Let's go ahead and let's see the next part of the grid, which is the transmission and the substation transformers, where we can see the power quality issues like the voltage sex propagation, or capacitor switching transients, lighting transients, or voltage transients, flicker, or unbalance, which can appear in the grid. If we go ahead, so the next one issue is connected with the distribution feeders. Basically the same things, the same phenomena like we were just discussing before with the transmission and the substation transformers. And the end user can face with inrush currents, grounding, or stray voltage, for instance, or this RESD technologies. RESD technologies basically stands for retrofit energy saving devices that are installed in order to improve the power factor, for instance, or the voltage imbalance, or energy efficiency, or to reduce the harmonics and the electrical current levels, for instance, or to ensure the cooler device is in a proper operation, etc., etc. And another things connected with the electromagnetic interference. So if one device is producing the higher harmonics, it can be damaging the other device or put it into malfunction, or maybe completely stop functioning of that device. So actually the electromagnetic compatibility should ensure that all devices are not interfering in between, and if some is producing some distortion, that is not in such a level which is putting another one into the malfunctioning, or the radio frequency interference might be another issue. And there might be some other issues, for instance, connected with the plug-in hybrid electrical vehicles, or in general with the smart grids or energy efficiency. Maybe let me to say a few words about the plug-in hybrid electrical vehicles, which is some kind of the devices which are in the focus of today's automotive industry, and which will be playing quite a significant role in controlling the smart grids, because this is some kind of the specific load connected, which will be connected into the grid. And the basic equation that is all the time required to be applicable for the electricity is that we have in a balance the amount of the energy being produced in the power plants and the amount of the energy being consumed by the loads. And it's quite hard to predict how much energy we have to produce because we don't know in every moment which kind of the devices are really switched on in the grid. So we have to have some other devices that we can connect in order or in a time when there is a lot of energy available that has to be consumed somewhere, or that can be switched off in a case if there is a lack of the energy. So this is the reason why the plug-in hybrid electrical vehicles are playing also the important role for controlling the grids in the future. If you look to that slide, so it's mentioning some issues connected with the customers suffering of the bad quality of the electrical energy. And it can be really very significant in a case if, for instance, the customer is running some kind of the technology which is very sensitive for the bad quality of the electricity. And there is not a single generic solution to solve the power quality problem. An optimum solution needs to be designed for each site, taking into account the above mentioned factors. So to be able to determine the source of the bad power quality, we have to have the measuring instruments which provide us the clear picture what's the reason or where is the source of the bad quality of the electricity, and then to find out the appropriate measure which will improve or which will remove that situation causing the bad power quality. Let's have a look to the next slide. This is the interesting table showing how big losses from the financial point of view are being caused by the bad quality of the electricity. It's showing some statistical numbers put together by the European Copper Institute in the survey which was done in 2002, and you really see the significant numbers, and it shows that it's really worth to invest into improving the power quality because it can bring a lot of the savings. The next slide is showing the grid. The grid in general, where we have the production, the power plant on the left side, and the consumption part on the right side. So the place where are our homes, for instance, connected into the grid. And the picture is showing the typical points where we should measure the quality of the electrical energy, and which can give us the very good picture of the power quality issues. Similarly, like Roberto was talking about the PMUs, so the similar situation is with the power quality analyzers. To really have a good picture what's happening in the grid, it's not sufficient to do the measurement just on one point, just on one side. Typically, we should have more analyzers which are doing the continuous measurement, measuring the data, doing the calculations of the parameters, and sending the data across, for instance, the internet to the power quality database server, which is storing the data from the multiple analyzers. And then we should have the software application doing the analysis of the data coming from the couple of sites. Who are actually the power quality customers? It could be the distribution companies having the power quality analyzers installed in the substations, or maybe using the portable power quality analyzers. In a case, if there are some complaints for the power quality coming from the users, coming from the customers, so then the power quality analyzer, which is portable, might play quite an important role, because the technician or the engineer who is responsible for evaluating where is the problem can take the portable analyzer to the site where some customer is reporting the problem. Another typical customers for using the power quality analyzers are the large industrial customers and engineering companies, and also the people working at the universities. They also are using the power quality analyzers for the research issues. ELCOM is dealing with the design of the power quality analyzers and the PMUs for quite a long time, and we have more than 17 years experience in the design of the power quality analyzers. The picture we are currently looking on is showing some types of the analyzers which we designed in the past, or which we are designing at the moment, bringing to the market, and where we use the technologies Roberto was speaking in detail before. And the typical features when using the virtual instrumentation technology are the high performance hardware, remotely upgradable firmware, or I/O expandable or multiple form factors, multi-ports and multi-protocols for communication support, and advanced embedded analytics and storage capabilities. Here we can see a couple of the screenshots of the software fully designed and developed in the LabVIEW. And when we started this area of power quality analyzers and the PMUs, so we actually we choose the LabVIEW as the platform for the design of the firmware, for the design of the software applications running on the PC for the analysis. And I think that it's showing a very good evidence that it was a good choice, because we were using all the benefits coming from the virtual instrumentation approach. So being able really to react very quickly to the demands coming from our customers, to the demands coming from the market, demands coming from the standardization or the international standards that are being continuously developed by the expert groups which are defining the standards. And using the LabVIEW allowed us to still be up to date concerning all these requirements. And also, in a case if there was some specifics coming from our customers, so also it was a good situation for us, because it took us a very short time to be able to come back with the solution of that requirement, specific requirement. Similarly, on the next slide, you can see some of the offline analysis tools that we have for the offline analysis of the data being measured by the analyzers and being stored on the database servers. Here is some example showing some projects that we deployed and that we have delivered to the major distribution and transmission companies operating in our market. So, for instance, company CEZ, CEZ, which is a distribution network operator, is using heavily the solutions for the power quality that our company has designed. Also, the German operator E.ON is using also the analyzers from our production, and the TSOs in the Czech and the Slovak market are also the customers using either the PMU solutions or the power quality solutions. The next, this slide is showing the map of the Czech and Slovak Republic, and it's showing how many of the analyzers or the measurement points we support in a Czech and the Slovak Republic. As the last example of the solution that we provided and that we are bringing it to the market is the project called WAMS, which WAMS stands for the Wide Area Monitoring System, and it's currently the project that we are delivering to the Czech TSO. which is based on the application of 39 PMUs and the WAMS central server located in the main control room of Czech TSO. And the reason of that project was to have a monitoring system which will be helping to the operators of the Czech transmission grid in order to see if the transmission grid is in a stable state, and if there is a certain reserve of the static power that can be transmitted across the main corridors of 400 kV lines used in the Czech Republic. And the reason for that, the decision for ordering that project is mainly being driven by the problems caused by the renewable power sources. I'm saying the problems, but when saying the problem, of course, I mean that it's unpredictable power sources, which very much depends on the sunshine, which very much depends on the wind, and of course, to be able to have still the power system in the balance. I mean, the balance means that the electricity generated and the electricity consumed is still in a balance. So it requires to have a more advanced measurement systems, and which is providing more advanced information in order to manage or to control the power grid and avoid the blackouts or avoid the islanding, which may appear because of that problem. This slide is showing the basic architecture of the system. We're having the PMUs installed on the substations, continuously measuring the values of the amplitude and phase of the voltage and of the current signals, and sending the data across the fiber optic lines from the substations to the main central server, which is storing the database of the data, and also running the analytics. And for the analytics, we are using the software coming from the Psymetrics company, which is the partner of us for that project. So it was the last slide from my side. So thank you very much for your attention, and I would like to pass the word back to Paul.
Okay, thank you very much, Dr. Kaminski. You know, as a mechanical engineer, I find discussions of these electrical topics absolutely fascinating. We'll get to some questions now. I want to remind you folks in the audience that it's your turn now to talk, or to type anyhow. So there's a little questions box in your panel to the right. If you don't see it, you just pick on the questions icon there, and it should pop open for you. Let's see, Dr. Kaminski, I have a question for you. How did utilities manage the power quality or gauge the power quality before the age of phasors, say 20 years ago? Did they have any idea of knowing whether they're getting good power out or not?
Well, if you mention that time period, 20 years or two decades back, so I would say that the problems with the power quality increases as more and more devices, which are switched controls, are being connected into the grid. So when having still less and less devices which are linear, so when having more and more devices which are providing the interference, so generating the higher harmonics, so it's still more and more becoming the issue. So before the PMUs and the power quality analyzers were available on the market, so of course there was not so big attention given to that problem, but recently, when the consumption of the electricity is increasing, when this appliances and devices being providing the distortion to the grid, or the EMC problems are becoming more and more important. So we are in the age where really without the proper monitoring and measurement systems giving the information back, it's almost impossible to have a safe managing and control of the power lines. Mm-hmm.
Yeah, I got the impression that when we had blackouts, you know, I think the utilities wait for us to tell them that the power is not on. So we were sort of the PMUs before the Phasor era. In any case, okay. Hey, Roberto, here's one for you. Now, as you add more intelligence and computing power to the grid devices, security becomes a major concern. How do utilities address this issue?
Well, this is a very interesting question, Paul. As I mentioned before, as we put more and more of this of these devices there, we are opening up the door for people like hackers, for example, to take control of those devices. And if you think about the financial impact of this bad intentioned people taking control of our devices, this is tremendous. Imagine that you have switches out there, you have reclosers, you have circuit breakers. Imagine that a person can just come in and then just turn off huge parts of a city, of even a state, if you will.
Yeah.
So basically, what we have to do here is utilities will have to gear up to make investments on the security area, which could include, for example, using proprietary wireless communications, or I actually worked in projects where they don't even trust this wireless technologies because of fear of hackers. So then they switch to fiber optics, and this is their proprietary fiber optics network, which is a lot more protected. We have to do things like firewalls. You got to do things like encryption, authentication. At that point, this literally becomes an IT problem. So in the future, utilities will have to act sort of as an IT company, managing all of these devices in the field, because in reality, they are computer nodes. They are network computer nodes that have to be managed just like any computer we manage today by our two departments.
I see. Okay. Well, here's another question for you. Okay, you're the popular guy today. Adding smart devices and enhancing the monitoring capabilities of existing grids will generate a massive amount of data. I agree. This is typically referred to as the big data challenge. And how are utilities addressing the issue?
This is another very interesting question. So this is, as you pointed out, this big data is the buzzword for now, right? You're absolutely right. One aspect to this is to we could mitigate this problem by adding more of this distributed intelligence I mentioned before, which is you don't stream all the data back to your SCADA systems, because this is obviously going to generate a massive amount of data. Now, if you do need to stream all this data, there's a variety of companies out there, such as IBM, Dell, and so forth, that are actively researching how to manage this. So then it goes back to my previous point of this IT challenge, right? So then utilities will have to engage with these big thinkers out there, these big companies out there that are doing this research, and implement server architectures, redundancy. They have to start thinking about data management, lifecycle management, right? They need to have, okay, I have this server, and this is the size of the server, this is how much data is going to grow, and they have to think a lot more about this data lifecycle management. I think in a nutshell, utilities are going to become more and more sort of like mini IT companies, if you will. It's going to become increasingly more sophisticated, their mechanics and how they operate, as we put more and more of these computer devices in the field.
I see. Okay, quite a problem. Okay, here's a question from Dr. Kaminsky. This is from Prashant, and he asks, what is a general cost for having these PQAs installed and have this system set up for a small grid system, for example, the microgrid of a university?
Well, I would say that it's very important to choose the appropriate architecture or the solution for the type of the grid or the type of the installation. And when I was mentioning that we have a suite of the software applications that can be used, so we cover from the large scale systems where having hundreds of the power quality analyzers being connected to the main server and storing the data on the server, and then evaluating the data on the server. And if we go back to some minimum installation, which can be even, let's say, 2 of the analyzers or even 1 of the analyzer, and this one is able to store the data locally on the analyzer storage media, and then you can download the data to your local computer and just run the simple post-processing application that will be analyzing the data from one analyzer. So this is the case where you do not need the server, and you don't need the database and some large application managing a lot of the data. So if talking about the some small grid or maybe some small application, so it's very easy to live with just the analyzers itself and the software applications which are automatically coming together with them. So then all the costs are just connected with the costs of the instruments itself, so no others. I don't know if it's sufficient to answer.
Well, I think he was asking about the specific costs, maybe the cost of a small PMU.
I think that maybe I can chime in on this one. I guess
sure.
Back to what Daniel was kind of saying. I mean, it will vary depending on the system, right? But the cost could range anywhere from a few $1,000s, like $2,000-$3,000, all the way to $10,000, depending on, for example, the number of channels you have, the type of measurements you want to make, the type of sensors you have. Because, for example, one point that we didn't discuss so much in here, but like sensors. Sensors are very, very important for those devices that are putting on the grid. And we need to put like big sensors out there that are able to measure hundreds of kilovolts, hundreds of kiloamps out there. So then those sensors are not cheap. So the power quality device itself, I don't think is a big chunk of cost there. And it can go, like I said, anywhere from $2,000 to $3,000 all the way to $10,000, depending on how many channels you have, what functionality you have, what type of sensors you have, and so forth.
Okay, all right, very good. Hey, Dr. Kaminsky, let me ask you then: would a power quality meter or the PMU, would that sit on the telephone pole or outside or would that be something in a substation?
If I understood well the question, it was about the how to transmit the data, or
well, the side. I'm curious about where the sensor, the PMU, would actually sit in the grid. Would that be on a telephone pole near the transformer? Or would that be back in the substation?
Yes. I see. Yes. That's right. As it was in one of my slides showing the basic architecture of the grid. So typically the power quality analyzers or the PMUs are being installed on the substation where you transform the voltage from one level to another one. So for instance, from 400 kV to 110, for instance, or from this 110 to the 22 or 6 kV, or to the next level from this high voltage, let's say 6 or 22 kV to 400 volts.
Okay, all right, thank you very much. Okay. Hey, Roberto, here's a question for you. One of the building blocks to smart devices is a sensor that allows most smart devices to connect to the grid. Okay, can you comment a bit on the importance or role of the sensors as we modernize the existing grid?
Great question. I mean, I tapped a little bit on that when I was kind of answering the other question. Basically, sensors are really the building blocks, and this is a very, very important aspect of PMUs, power quality, or any device you're putting out there for making measurements. And oftentimes, sensors are an afterthought. Right? So it doesn't matter if you get a PMU or power quality with 0.1% accuracy. If you get a sensor that is 10% accurate, your measurement is going to be as good as your sensors are. We did some research, and obviously I'm not going to say which brands we measured and we validated, but we saw a great difference between quality of sensors. We saw some sensors that were 1% accurate all the way to 10%. Think about it, 10%, Paul. It's a large number. Imagine that you are making decisions on how to isolate parts of your grid, or if the quality is good or bad. And 10%, it's a lot of error. So sensors are very important, and I think that it should be brought to the forefront of projects when designing what to monitor, where to put this in the grid. Sensors should be the very first thing that you decide, and then you go match the sensor accuracy with your equipment quality accuracy as well. But again, keep in mind, your measurement is only as good as the overall system is accurate. So then it doesn't matter spending hundreds of thousands of dollars on very accurate equipment if your sensor, it's inaccurate.
I see what you mean. Okay. All right. We just passed the 3:30 period. Gentlemen, we're running out of time. And once again, let me remind the audience that the webcast will be available for reviewing at windpowerengineering.com. And one final message, you can follow Windpower Engineering and Development on Facebook, Twitter, and LinkedIn. So this concludes our presentation. I want to thank everyone for their attention, and from the staff here at Windpower Engineering, we wish you a good and productive afternoon.